Hello and welcome to the second lecture of our course on communication network analysis. We will continue following chapter 2 of Shrikant and Ying's book. So in this lecture, we will first review convex optimization and then apply it to some utility maximization problems in networks. So we will consider the standard constrained convex optimization problem stated as maximizing a function f of x over a convex set S subject to some inequality constraints and equality constraints given by hi's and g sub j's for an arbitrary number of inequalities and equalities. Okay, now for this convex optimization problem, we can define the Lagrangian as the following. Lagrangian is the function f of x minus the summation of some parameters lambda I times hi of x for each of the inequality constraints hi, and summation mu sub j, g sub j over all the equality constraints. Now, the constants lambda I and mu j are called Lagrange multipliers. The Lagrangian dual function is defined to be this function d, which is the supremum over the set S of the Lagrangian. Okay. Now we will first discuss some useful properties of the dual function and then apply them to our to facilitate our convex optimization problem solution. First of all, define f star to be the maximum of the optimization problem, the original optimization problem. Okay, theorem 211 from the textbook says that the Lagrangian dual function is a convex function and its value is never below f star. Okay, so it is obtained as a result of the supremum. That's, you know, if you look at the proof, taking the supremum here results in essentially this result, and I recommend that you read this proof here, and you can find it in the textbook. Now, let's define the Lagrange dual problem. The Lagrange dual problem is the problem of the unconstrained optimization of the Lagrange dual function, which is the infimum over the Lagrange multipliers of the Lagrange dual function. Now, why is the Lagrangian dual function only a function of the Lagrange multipliers and not a function of the free parameter x? Well, because we've already optimized, remember, we've already optimized over x, essentially. We found the supremum over the set S. So now this is only a function of the Lagrange multipliers, and now we go ahead and make it as small as possible over the choices of Lagrange multipliers. Because of theorem 211, it will give us an upper bound on the original objective function. The infimum will thus provide the tightest upper bound. Okay. Now, suppose d star is the minimum of the dual problem. Okay, d star is the result of this optimization, that is. The difference between d star and F is called the duality gap. Okay? For some problems, the duality gap is 0. We say strong duality holds if the duality gap is 0. In that case, one can either solve the primal problem or the dual problem to obtain F star. This is helpful as often one of the problems is easier to solve than the other. A simple and frequently used condition is to check strong duality is Slaters condition. Now, what is Slaters condition? It says the strong duality holds if the following conditions are satisfied. First of all, f of x is a concave function, okay, and hi of x, the inequality constraint functions, are convex. The g sub j of x are affine for all j. Moreover, there exists an x that belongs to the relative interior of S such that hi of x is less than 0 for all I, and g sub j of x is 0 for all j. So in this case, strong duality holds, and this is known as Slaters condition. Now let's talk about the Karush-Kuhn-Tucker conditions. Consider the constrained optimization problem that we've defined. Assume that f and hi are differentiable functions and that Slaters conditions are satisfied. Remember, Slaters conditions are about the convexity of the hi's and the affineness of the gi's, essentially, in addition to this third condition, that there exists an x that belongs to the relative interior such that the inequalities are satisfied strictly and the equality conditions are also satisfied. Okay. Now, if Slaters conditions hold, and moreover, if f and hi for all I are differentiable, then for any feasible point x star, such that the constraints are satisfied, x star is a global maximizer for the optimization problem if and only if there exists Lagrange multipliers lambda I star, non-negative, and mu j star, such that when you differentiate the basically the Lagrangian function with respect to the parameters xk's, the free variables, that is xk's, you get 0 for all k and lambda I star times hi x evaluated x star is 0. Okay, so now these 2.8 and 2.9 are also necessary and sufficient conditions for the pair lambda star mu star to be a global minimizer of the Lagrange dual problem. Now, if f is strictly concave, okay, then x star is also the unique global maximizer. In general, if f is concave but not strictly, then it is possible for multiple maximizers that achieve the same objective function. However, when f is strictly concave, then you know that x star is the unique global maximizer. Now, what is the interpretation for the KKT conditions? Well, if you consider the Lagrangian here, condition 2.8 is the first order necessary condition for the problem of the maximization over S of the Lagrangian. When strong duality holds, okay, if that condition is satisfied, we arrive at this, which results in condition 2.9. Okay, 2.9 is also called complementary slackness. So all of this is really note that something that you've already been doing in the optimization of one-dimensional functions, right? Differentiate and set it to 0, and then check that the point you found is within basically the space that you're optimizing over. And sometimes sometimes the optimizing point could be at one of the boundaries, okay? And that is taken care of by 2.9. Okay, now we will apply convex optimization to resource allocation as a utility maximization problem. Consider a network consisting of a set of links L accessed by a set of sources S. The terms source and user will be used interchangeably here because each source corresponds to a flow between a source destination pair, and we assume that there is a user that is interested in this flow. Okay. Moreover, each source is associated with a fixed route. We do not, without loss of generality, really, we do not consider routes that are shared by different sources. I mean, it would not be hard to extend this to a more general model, but for now, for simplicity, we will assume that each source is associated with a user and with a fixed route. Okay, what is a route? A route is a collection of links from source to the destination. We're going to use the same index to denote a source and its route. Okay, because we want to keep the problem simple for tractability. Of course, all of these are very easy to generalize once we see the solution. We are going to allow multiple sources to share exactly the same route, but we will name those routes differently. Okay, even if they consist of the same set of links. Okay, so when two routes consist of exactly the same set of links, they will be still named differently. Now, the user R attains a utility U of X sub R when it transmits at rate X sub R. Okay, now we will consider the case that U is a monotone increasing, continuously differentiable, and concave function. Okay. So what is the notion, what is the logic behind this? In a lot of network settings, it is very intuitive that as the rate increases, the utility derived by the user will increase. This may not be the case in all possible scenarios. However, in a lot of classical network settings, when the rate is increased, the utility drawn from that flow does not decrease. Okay. A caveat is maybe the age of a flow, but that is different.